we will look briefly at some aspects of the power architecture. First, it is the commercialization of the IBM 801 research prototype led by John Koch. And one interesting thing is that it was a power machine that was the first computer to beat a chess world champ in 1997. Okay, Power 4 was the first chip with 2 cores on it, so it was the first chip multiprocessor. The Power 8 that we use has 10 cores. There are versions with up to 12 cores and 96 threads per chip. And some can be clocked at 5 gigahertz. Ours can be clocked at 3.5 gigahertz. Okay, and it has 10 cores and each has 8 threads. There was a recent machine in August, Power 10, and it has it's produced with 16 cores and 15 of them are available, and the 16th is for not used normally. It's for to give better yield. So 16 are produced, but the intention is to use 15 of them. And the trend for Power is to add more support for AI workloads, and to be able to address that means in a simple load instruction we can select 1 byte out of 2 petabytes if we have that amount of memory in the machine. Okay, so this is partly a repetition. We will look at the aspects of the power architecture, and well, we will go on. And I will not ask you details about this, but it is important to understand the ideas with RISC, pipelining, and superscalar processors. And for that we use Power as an example, and you will use Power on the labs and in the project. Okay, so there are these 32 registers of different kinds, integer, and it's called general purpose registers, and they can have integers and addresses, and floating point and SIMD registers. Then there are some special registers that can be used, for instance, as a loop counter, or to save the function call return address, instead of wasting one of the 32 general purpose registers for the return address. Okay, this register is called the link register. So if we call printf, it is this instruction, bl branch and save the return address in the link register. And then there are instructions to transfer the value of this link register to or from a normal register so that it can be saved on the stack. The count register, it can be used to avoid incrementing I in a loop. So we can calculate, or the compiler calculates the number of iterations, and then it moves this number into this count register, and it will repeat this statement S until the count register becomes 0. So this is branch, decrement, and branch if it's non-zero. Okay. And to make comparisons, there are 4 bits used. Well, actually 3, but there is a 4th. To compare 2 integers or floating point numbers, the result can be that one is negative or positive, or they are equal. And there is a 3rd bit for summary overflow. That is, if this bit is set if when we did an add instruction there was an overflow. Okay, and there is an array of, well, there are 32 bits for such, so there are 8 condition registers, each with 4 bits. Okay, and there's one for that is default for integer registers or integer instructions, and another default for floating point. Okay. Well, this is a normal floating point register. We will come to that later on. Okay, instruction formats. We talked about one instruction format the previous time, namely to do an add. But there are this constant field of adding a constant. It had 16-bit constants. I mean, in the version that had an immediate operand, but that is too small for making a function call, because we want to be able to jump far ahead in the program or back in the program. So therefore there are different formats for different purposes, and the first 6 bits say what we should do with the rest. So this branch and link instruction, it has almost all of the bits reserved for how far we should branch. Okay, I will not go into the details of this, but I should say something about integer numbers. Unsigned integers, they are represented as we are used to, and signed integers, they are represented in something called 2's complement. And what we do is to say we have a 4-bit register. So we have 4 bits to represent either a unsigned or a signed number. Then the unsigned from 0 to 15, they can be represented just as expected. But the signed, they are, first of all, it's not the symmetrics, since we go from -8 to 7 and not from -7 to +7, for instance. Okay, so how are they represented? We store them as for this 4-bit field, we store them as 16 minus the value that we want to negate. So to have 5, we use 4 plus 1, but to store -5, we store 16 minus 5. Okay, and what is that? Well, this is 16 and that is 5. Okay, and we will use only 4 bits. So how can we calculate what we should store? Well, this 16, it can be written as 15 plus 1, and then we subtract. Doing it like this makes it easier to subtract, since we can use all the, I mean, we don't have to borrow from any other position. We can just subtract this from that one, easy, and then add 1. Okay, so we get this 11. I mean, interpreting this as an unsigned, it's 11, but interpreting it as signed, it's -5. Okay, another way to look at this is to say that for a signed integer, this position has the value -8, and the others are positive. I mean, if there is a 1 there, then that position is worth -8. That's 0, and then we have 2 and 1. So it's -8 plus 2 plus 1 equals -5. And an advantage with this is that if we have -5 plus 5, we should get 0. And if we do that with and just keeping the 4 bits, then we get 0 as we hoped for. Okay, so then we have an interesting question. What does this mean? We don't know, because we must know the type. We must know if this is a signed or an unsigned integer, and the compiler will decide which kind of instruction it will use, for instance, in a comparison, depending on whether the operands are signed int or unsigned int. So we have 4 types of integer compare instruction. Signed compare with registers, signed compare with one register, and the other sign extended immediate. What does sign extended mean? Well, if we have this -8, recall -8 is where did we have it? Well, it's 1, and here it is. This is -8. Okay, but if we want to represent this as, for instance, 6 bits, what can we do? We can just duplicate this bit. So we take that bit and duplicate it here. And what does that mean now? It means still that we take the leftmost and treat it as a negative. So that one is -32 plus 16 plus 8 is -8. So we can duplicate the most significant bit without changing the value. Okay, so why do we want to do this? Well, we want to have as many bits in this operand as we have bits in the register. Otherwise, we cannot compare a 64-bit register and a 16-bit constant unless they are, I mean, we must do this sign extensions so that we have 2 64-bit numbers to compare. Otherwise, we get the wrong result. And there are unsigned compare, meaning that we interpret all the bits as if they are in an unsigned type.